Okay, hello and welcome to the part 3, which is fault tolerant broadcast. So in this previous challenge, we implemented the multi-node broadcast, and this is the extension for that. So in this challenge, they have introduced a new constraint, which is network partitions between nodes, so they will not be able to communicate for a period of time. So this is the only constraint that they have introduced. Let's also go through other specifications. Your node should propagate values it sees from broadcast messages to other nodes in the cluster, the same in the previous challenge, even in the face of network partitions. Values should propagate to all the other nodes by the end of the test. Nodes should only return copies of their own local values. Okay, and for this challenge they have introduced this partition, which will be validated by the Maelstrom library. So in this challenge also we have a 5-node cluster like before, but with a failing network. So let's see how we can solve this. Okay, so I have created a diagram. So this is our system. So now we want to perform inter-cluster communication, but it will be not available for some period of time. So if some functionality is not available for a period of time, we can repeat it after it's available, or we can keep doing it. So unless and until it is, we can keep repeating the internal messages, and we don't need to know whether it is going through or not. So what we can do is, instead of sending a new message from the broadcast, we can send all the messages from a current node to the other node. So what I've introduced in this is, instead of sending a new message, I am sending all the messages from the current node to the other nodes. So n1 will send all its values, which are 10, 20 and 30, to the node n2, and this it will send repeatedly. So let's say if after every 1 second it is going to send these values. So what this ensures is, even if let's say for the second during the second 4, 5 and 6, the network partition is introduced, but we are sending it after every second. So even if the messages during the fourth, fifth and sixth second don't go through, we are sending it again in the 7th second, 8th second. So this will ensure that the consistency is achieved. So if you looked at the implementation of the multi-node broadcast, we are sending a new message, and this new message is from the broadcast message that we have received. But as we know, this message may not go through. So let's say at some point this network partition is introduced, so this message cannot go through and it may fail. So you can even run the same program against this command, and you can see that it fails. Okay, so what the solution for this is to send all the messages. It may not be efficient, but for this challenge, let's say we are implementing this because it is a working solution, and for the part 4 and 5 we are required to optimize our solution, so we'll go for the optimization later. So the basic idea is to send all the messages from a current node to the other node in repeatedly in some frequent interval. It could be 1 second or 500 millisecond or 200 millisecond, depending on the it may give different result if you experiment with those values. So let's see how network partitions are introduced and how our system is going to stay consistent by following eventual consistency paradigm. So as we introduce these type of messages, so let's assume there are two nodes, and the same example that we took in the previous challenge, client 1 sends a message 10 to node n1, and another client sends message 20 to node n2, and now we are going to send all the messages from current node from one node to other. So assume this arrow represent this message, and from n to 10 1 represent this message. Now let's say during this period, so whatever I have graphed here, during this period a network partition is open. That means these two messages don't go through. So these two messages don't go through, but our algorithm, what it does is it is going to retry sending those messages, or it will send those messages after every 500 milliseconds. So 500 milliseconds have passed, we are again going to send those messages. Again after 500 seconds we are going to send those same message. Eventually network partition is opened. Network partition is not consist I mean always closed, it is temporarily closed. So let's say after the interval when network partition is removed, the messages start going through. So once this phase occurs, the messages will go through, and as you can see, the state of the node remains the same during the network partition. So it during the network partition, node n1 contains value 10 10 10 always, similar for n2. But after the network partition is closed, we can see that the internal messages go through and the consistency is achieved. So when these messages go through, the values in the node n1 will be updated to 10 and 20, and similar for node n2. My bad, here it should be n2, can assume that. So this was how network partition was introduced, and this was the solution for this, the main idea. Now let's go to the implementation. So this is the fault tolerant broadcast. Everything remains same, we even keep the same format, but instead of sending a new message, which we were doing in this, here we are sending a new message from the broadcast. We are sending all the messages in the current node. So what we need to do is initially, so to achieve this, that we after f500 every 500 milliseconds we need to send a message from one node to other. Again we use concurrent programming or multi-threading to keep two threads running. One is the main thread, which is going to perform request and response communication between client and server, and the other thread which is going to perform internode communication. So this messages is our data store, or we can say the list which store all the messages in this node. And I'm creating a atomic reference counting clone for it, because we need a reference for message in the secondary thread as well as the main thread. So to pass the values as shared mutable references. Now we need to extract the node ID and the node IDs of the other nodes in the cluster. I'm going to process the init message initially and get these two values from them. After that I will go through this code later, because this is the operation of the second thread, which is sending the internode messages in some frequent interval, which I have used 800 here. So again the init message was already processed, so I just used some error handling here. After that read message comes, we can use the mutex lock to, since messages is shared between two threads, this one and the main one, so we need to assure that only one thread has a mutable access to these messages. So we lock it and we clone and send it to the read response using read OK body. After that a broadcast message comes, we insert it into our messages hash set and send the corresponding acknowledgement message as broadcast OK. Topology we are not using, since there were only 5 nodes. We can use this optimization for the part 4 and 5. Again internal messages come, it is a hash set all messages, so we just extend our current nodes messages with the messages that were passed by some internal message by the other node in the cluster. Other parts remain same. So as you can see here, we never invoke our internal message after client server message. Our internode messages are completely independent, and it is you can say it is a multi-threaded application. One thread runs on its own, second thread performs frequent operation one after the other. It functions in one thread are not invoked by responses or requests in the other thread. So this is a batch thread to send current nodes all messages to everyone in the cluster. Again, so this is not the best approach. You can even experiment with it and try to optimize it further. So what it does is it spawns infinite loop, and it is going to, let's say, after every 800 milliseconds uh, perform this operation. This operation is sending all the other nodes. This is iterating over all the other nodes and sending an internal message. Let's see what that internal message is. Internal message, this message is obviously the hash set is shared between two threads. So this hash set, we created a reference, this reference for the main thread and this for the secondary thread. So whenever we want to access the values in that hash set, we need to acquire a lock always. So even if we here wanted to change the values in that hash set, so we acquired a lock, then we updated that hash set. Again, this whenever this lock is dropped, scope of this is locked, then that mutex will be unlocked. So we don't need to manually unlock the reference to our mutex. After that, so my message is acquired here, the lock is acquired, we clone it and send it as an internal message. And as you can see, this operation is continuously performing after every 800 milliseconds. So even if some messages are dropped, eventually they will the values will get propagated after some time. So I have used an explicit drop here, which was not necessary, but eventually, so what initially I did was this thread sleep was present here. So so I was not dropping the acquired mutex lock. So what happened, the scope was not over and it went on to sleep for 800 milliseconds, but the drop was not locked. So for 800 milliseconds, this lock couldn't perform, like it was idle, and this main thread couldn't acquire it. So that was a little bit educational for me. And after that, again, this is going to print the internal message to the standard upload for the validator to judge. Okay, so there were some concurrency concepts which were also useful, like shared mutable data between threads. And in the previous challenge also we used channels for inter-thread communication. So yeah, it was good to go through some solutions in Rust, and this is a good source for learning Rust as well. So that's it for this challenge. There might be various different beta algorithms, so you can even read about gossip algorithms for achieving consistency in distributed systems. You can there are so many different ways to solve this challenge. So I've just shown you one way, and you can experiment with the rest of the thing. Next, I wanted to show you the results. So I've run this already. As you can see, I've run it multiple times, and there is this results, and I wanted to show messages. Okay, so the results, as you can see, for this challenge also we are this information or results give us some insights about how many operations are how many messages are being transferred between nodes and clients. So client has sent 450 messages and it has received all the 450 messages because our at least one of the nodes in the cluster is going to respond to those messages. That is the guarantee for this tester. But the nodes I mean the messages sent between servers were not all going through. So 760 were the total messages sent between servers and only 572 went through. So you can imagine that the difference of these values were the messages during the network partition, right? And these were the messages per operation value. There are other constraints as well which are not very important. And since this was uh, since we were sending all the messages, it was not very optimal. So as you can see, the latency is almost 3 seconds. I mean, the maximum time our uh, it took to come to a consistent state was 10 seconds. So this is clearly not optimal. So you can even think of other approaches as well, or we can optimize it in the next part. So 50% of the time our latency was about 3 seconds, 3000 milliseconds. And in the later challenges as well we need to improve this. Yeah, so this was the result. Next one is this diagram. So as you can see, there were 5 nodes in our cluster and about 10 clients, and these were the internal messages that we are sending. So this random, it's not random but chaotic messages that are sent between nodes you can observe here. So after every 800 milliseconds this thing is going to take place. Every 800 milliseconds this is going to take place, and all the messages are served in between. And you can see that no internal messages are invoked after a certain client message. They are performing those communication on their own in those intervals. So you can see all these messages are being passed and the states may be getting updated. So this is how distributed systems work. Clients and servers need to perform these operations and servers need to come to a consistent state. This challenge is about that. Okay, so that's it for this video. Hope you like it. I will solve the remaining part and create a walkthrough for that. Thank you.